Manyuan Tao will speak about modeling fracture of hydrogels or fracture of polymer networks. This is a joint work with Zhigang Suo's team from Harvard. So collaborators are Manyuan Tao, Zhigang Suo, Sean Lavoie, and myself. So I am starting sharing screen. Full screen, and this you put here, and this one.
Hello, my name is Manyuan Tao. Our project is modeling the fracture of polymer networks.
Window.
Yes. A comparison between two highly elastic materials, the silica glass versus a polymer acrylamide hydrogel, was given in the work of Yang and Suo. They both fracture by breaking covalent bonds. However, the experimentally measured strength is typically orders of magnitude lower than the covalent bond strength. Here, the strength of a material is the maximum applied force during stretch of the material up to complete fracture, which means that the top and bottom boundaries belong to two disconnected parts. The low strength of the silica glass is known to be caused by crack-like force, which deconcentrates stress, but the low strength of hydrogels still needs to be explained. In recent years, hydrogels found numerous biomedical applications, and also in other spheres of industry listed on the right. The hydrogel is a polymer network swollen with water. A real polymer network is never perfect. Shorter chains, longer chains, and dangling chains are coexistent in the network. This fundamental difference in the structure between silica glass and the polymer networks initially drew our attention. Why is the measured strength of a polymer network so low compared to the strength of covalent bonds? We hypothesize that the large reduction in strength is caused by a J-shaped stress-stretch relationship and statistical variation in lengths of polymer chains. We test these hypotheses using two simple models. One is a parallel chain model, where a large number of polymer chains of different lengths are attached to two rigid plates. When the two rigid plates are pulled by a pair of force F, all the polymer chains are stretched to the same distance Z in parallel. Another one is a 2D truss model, where an array of nodes are connected into a diamond grid through the polymer chains. A typical J-shaped stress-stretch relationship is given by the Langevin function. The Langevin function corresponds to the mean displacement of the chain in the direction of the force for a freely jointed chain. Here, n is the number of Kuhn segments in the chain. Later, the Langevin function was modified with a stiffness to fit a measured force extension curve for a hydrogel, which is in the black graph here on the bottom right. This modification allows Kuhn segments to stretch before rupture. However, both of the two Langevin functions give a zero chain length when the force is zero, which is not suitable for our simulations. In order to obtain a non-zero chain length, we derive the root mean square deviation for the following two quantities. First is Rn, which is the end-to-end distance of the polymer chain. Another is the ZRMS, which is the displacement of the chain in the direction of force. We employ ZRMS as our stress-stretch relationship. And we obtain the initial displacement as square root of n over 3. Here n is the number of Kuhn segments in the chain. So far in this ZRMS, we obtain the stretch as a function of the applied force F. However, we need the inversion, which is the stress as a function of stretch. Therefore, we further invert the ZRMS. We obtained the inversion for ZRMS and also made a close approximation for the inversion. Our approximation is based on the most popular Cohen approximation. The purple curve in this figure is our approximation for the inverted ZRMS. The breaking force for a single chain is 200, which is normalized from the experimental work by Zhang Zhou. The experimental work for the modified Langevin function here. We also introduced a scatter in the lengths of polymer chains. We vary the number of Kuhn segments per chain according to a shifted and discretized Weibull distribution, shown in the figure on the left. The Weibull distribution is chosen because the actual chain length distribution measured in a recent experimental work was found to be similar to a Weibull distribution. Next are our results for the models. For the parallel chain model, we calculated the mean force at the top using this formula. Here, F of NZ is the stress-stretch relationship. We study 3 different types of the stress-stretch relationships: the Langevin function, the Langevin model, the modified Langevin model, and also we studied the linear model for comparison. The P of n is the probability for the number of Kuhn segments. We plotted the mean force for 3 different types of model versus the distance z between the 2-digit plates. By comparing the maximum of the mean force to the breaking force of 200 on each single chain, we can see that a large reduction in strength is obtained for the 2 Langevin models, which have the J-shaped stress-stretch relationships. By comparison, the linear model does not reduce the strength as much. Also, we can see that as the scatter in the chain lengths is increased, the strength is further reduced. We also plotted the maximum mean force, which is the strength, as a function of the variability, which is the standard deviation normalized by the mean. The variability is a dimensionless measure of the scatter in chain lengths. A power law relationship is observed between strength and variability. The least squares fits are given here. This motivates us to study the derivation of this power law for the parallel chain model. So in our derivation of the power law, we replace the discretized Weibull distribution by the continuous one. Therefore, the mean force is given by an integral here. We derive the power law using 3 steps of approximations. First, we approximate the stress-stretch relationship, which is the function f of nz here, by a piecewise constant function. Secondly, we approximate the maximizer of the function, the mean force function f of z. For this approximation, we found a correlation between the z max and the medium of the y-ball. Finally, we relate the k and lambda, the 2 parameters in the y-ball distribution, to the variability. We found a power law between the parameter k and the variability.
What is parameter k?
K is the shape parameter in the y-ball distribution. Here are the detailed formulas for our approximations. We use the modified Langevin model for illustration. First is the piecewise constant approximation to the stress-stretch relationship. Second is our approximation for the maximizer. Finally, the shape parameter k relates to the variability via this power law. And also for the scale parameter lambda, it's just approximately equal to the mean mu. Using these 3 approximations, we predict the power law as follows. We can see that it's a super close approximation to the empirical result for the modified Langevin model. Besides, for the truss models, we also obtained an empirical power law. For truss models, we experimented with 4 different truss sizes: 20 by 20, 40 by 40, 60 by 60, and 80 by 80. So the power laws are obtained. The prefactors are the same, but the powers slightly reduces as the truss size goes up. Finally, we conclude that it is the combination of a scatter in the lengths of polymer chains and a J-shaped stretch relationship that leads to the small variability in strengths between samples and also a large reduction in strengths compared to the covalent bond strengths. Our future work includes the following directions. Currently, the 2 models do not account for these spontaneous breakage of polymer chains, which we can include in our simulations later. Also, we can consider the localization of deformation and the concentration of stress in the polymer networks. In addition, we can further generalize our derivation of the power law to a family of distributions that are similar to the y-ball distribution.
Thank you, Manyuan.
Yes.